Hi everyone, welcome to part 2 on our video recording for section 11.2, Properties of Power Series. In the last recording, we went over the definition for a power series, and we went over one example dealing with the interval of convergence. In this part 2, we're going to go ahead and take a look at more examples of power series and find their interval of convergence, as well as discuss some useful properties that we can use to combine power series. So let's go ahead and take a look. We begin with the following power series. The sum as n goes from 1 to infinity, for negative 3 to the n times x to the n all over the square root of n plus 1. Alright, so first things first, where's the center for this power series? Well, since I'm not adding or subtracting anything to the x, it seems like this power series is centered at x equal to 0. Okay, so now let's go ahead and use the ratio test to determine the radius of convergence. So we're going to have here the limit as n approaches infinity for the absolute value of the nth plus 1 term over the nth term. Alright. So now let's go ahead and start simplifying here. So we're going to get here the limit as n approaches infinity for the absolute value of negative 3 to the n times n negative 3, again by splitting up the powers here, times n x to the n times x, again same thing, times the square root of n plus 1 all over the square root of n plus 2 times n negative 3 times x to the n. Now we get to see here that a couple of factors cancel out here, so we have a negative 3 to the n, and whoops, I did miss the n here, there we go. Now it cancels out. I see another x to the n that cancels out. And let's take a look. Does anything else cancel? It doesn't seem like it. So let's see. We're now going to get the limit as n approaches infinity for the absolute value of negative 3 times x times the square root of n plus 1 all over the square root of n plus 2. All right. Now once more, since we're taking the limit as n goes to infinity, the x is pretty much unaffected by the limit. So I'm going to go ahead and take it outside of the absolute value, as well as the negative 3. Now, since we're taking this outside of the absolute value, remember they're technically still within an absolute value, and the 3, since it's just a constant, negative 3, its absolute value is just 3 times the absolute value of x times the limit as n approaches infinity. But now at this point, since I do notice that I have a square root on the top and a square root on the bottom, and square roots, I know by definition, give us the principal root, a positive, I'm going to go ahead and drop the absolute values, and I'll rewrite the square root of n plus 1 over the square root of n plus 2 as the square root of n plus 1 over n plus 2. Okay, now because we do want convergence, we set up our inequality here to be less than 1. Okay, perfect. We're almost done. Now we just need to go ahead and evaluate this limit. Now, what is going to be the limit for the square root of n plus 1 over n plus 2? Sure, we could use L'Hopital's, but we can also remember that when we're working with limits and we're dealing here with a function composition, we can just as easily just take the limit as n approaches infinity for the argument of the square root, the n plus 1 over n plus 2, and we know that, hey, this limit is simply equals to 1. So then what we're working with is 3 times the absolute value of x, now times the square root of 1, which is going to be a 1, and this whole thing then is less than 1. Perfect. Now we have enough information to figure out our radius of convergence. It seems like the absolute value of x has to be less than 1/3. And here is our radius of convergence. So thinking about the number line, how far away can we get from our center at 0? It seems like we can only move a distance of 1/3 to the right and 1/3 to the left. All right, so we get to see that we have absolute convergence for the values in between a negative 1/3 and a 1/3, but now the question becomes, are the endpoints included? Well, back to the usual drill. Once we figure out our radius of convergence, yeah, we got to check for the convergence at the endpoints. Okay, so let's see. I guess before we take a look at one example, I do want to emphasize that yes, the radius of convergence is 1/3. All right, so let's go ahead and begin by taking a look at the left endpoint. At negative 1/3, do we get convergence? Or when x is negative 1/3, do we get convergence? Let's go ahead and take a look. So at x equals to negative 1/3, we have the following series. The sum as n goes from 1 to infinity for a negative 3 to the n times a negative 1/3 to the n all over the square root of n plus 1. All right, so I get to see that I have a negative 3 to the n and a negative 1/3 to the n, so I'm going to go ahead and combine them inside a single parentheses. So we have the sum as n goes from 1 to infinity for a negative 3 times a negative 1/3, well, notice that basically we're now just left with a 1, and it seems like it's a 1 to the n, which is always going to be a 1, and it's divided by the square root of n plus 1. So with our final simplification, we're left with a series as n goes from 1 to infinity for a 1 over the square root of n plus 1. Now, is this series converging or diverging? I want you to pause the video and think about which test you would use to show divergence or convergence, and then we can compare our answers. So let's go ahead and pause. Welcome back. Did you get divergence? Well, I did. What I opted to do was to compare the series as n goes from 1 to infinity for 1 over n plus the square root of n plus 1 to the series as n goes from 1 to infinity for 1 over the square root of n, which was a diverging p-series because it had a p-value of 1/2, which was less than 1. Then I opted to use the limit comparison test. Again, that was my own personal preference, and I ended up getting 1 as my limit, which is a positive finite value, which means that both series have the same behavior. So they will both be diverging series. Now for this example, you could have also used the direct comparison test, and you would have obtained the same result. Okay, so now let's take a look here at our right endpoint. At x equals to 1/3, we obtain the following series. The sum as n goes from 1 to infinity for negative 3 to the n times 1/3 all over the square root of n plus 1, which, whoops, I did miss another n, there we go, which can be simplified to the series as n goes from 1 to infinity for negative 1 to the n all over the square root of n plus 1. Now, in this scenario, we are dealing with an alternating series, which means that we can go ahead and use the alternating series test. Now, this one here will be left as an exercise for you, but if you go ahead and use the alternating series test, you would see that you indeed get convergence. Now, this is where we're going to go ahead and mention that when you're dealing with the endpoints, it doesn't matter if you get conditional convergence or absolute convergence. As long as you're getting convergence, that is good enough. So I listed here that, hey, yeah, at the endpoints, conditional convergence, that's it, you're good to go. Okay, so now we can go ahead and give the interval convergence for this particular series. The interval of convergence for this one here was from negative 1/3, and at that endpoint we did get divergence, all the way to the 1/3. In fact, let me go ahead and put them here in plum. There we go. We're done. Excellent. Okay, so now I want to go ahead and take a look at 2 more examples, although these ones here are going to be a bit shorter. Let's go ahead and take a look at this next problem. We're given the following series as n goes from 0 to infinity for n factorial times x to the n. Alright, so where is this one centered at? Yep, it's centered at 0. So now let's go ahead and use the ratio test. And we're going to get here the limit as n approaches infinity for the absolute value of n plus 1 factorial times x to the n plus 1 all over n factorial times x to the n. Alrighty, so let's go ahead and do some simplification here. So rearranging the terms, we're going to get the limit as n approaches infinity for the absolute value of. Now for the factorials, remember, the factorials were a special type of multiplication where you're multiplying a number times its previous positive integers. So if I have an n plus 1 factorial, then the n plus 1 is multiplied times the previous term, which is an n factorial. Now the previous one would have been an n minus 1 factorial, but I'm going to stop here because I notice that in my denominator, I do have another n factorial. Great. Now let's go ahead and continue. On the numerator, I still had the x to the n plus 1, which means that I have an x to the n times an x. And this whole thing was also being divided by an x to the n. All right, perfect. So I get to see that the n factorials cancel out and the x to the n's cancel out. So now we're left with the limit as n approaches infinity for the absolute value of x times n plus 1, which is going to give us now, let's see, the x can be taken outside because it's not affected by the limit. And we're multiplying that times the limit as n approaches infinity for, and again, at this point, since I have an n plus 1, and I know that the n's are all positive here, I'm going to go ahead and drop the absolute value. So now I just have the limit as n approaches infinity for an n plus 1. And if we want convergence, then this whole thing must be less than 1. Now, is that a problem? Well, I would say that maybe, Because what's the limit as n approaches infinity for n plus 1? Well, this whole thing is just going to go to infinity. And, well, that's not less than 1. So what is this telling us? Well, I would argue that there's only one value for x that would make this inequality true. Only if x is equal to 0, then your inequality is less than 1. But for our problem, well, it was centered at x equal to 0. So what we're seeing here is that you're only getting convergence at the center, which means that the radius of convergence for this problem here is equal to 0. So this is one of those cases where, yeah, the series would not be particularly used for full analysis because, yeah, it's only converging at the center. So it's not very useful. Okay, so let's go ahead and take a look at one more problem where we're finding the interval of convergence. And this one here is the following series. The series as n goes from 0 to infinity for x to the n all over 2n factorial. Okay, so once more, where is this particular series centered at? Well, again, it seems to be centered at x equal to 0. Okay, so let's go ahead and use the ratio test once more to see what we get for our radius of convergence. So we're going to get here the limit as n approaches infinity for x to the n plus 1 over, and now this is where I want you to be careful here, because we are dealing with factorials, and what we're actually working with is 2n factorial. So I have to write it like this, parentheses 2, then I'm getting the nth plus 1 term, so it has to be 2 times n plus 1 factorial. This is very important because it is going to make a difference in your answer. You got to be careful there with the parentheses. Okay, now times, now again, it's just the reciprocal of the original nth term, which is going to be a 2n, parentheses here, factorial all over x to the n. Okay, now let's go ahead and start rewriting it so we can simplify it. So we're going to get here the limit as n approaches infinity for the absolute value of x to the n times x times 2n factorial on the numerator, but in my denominator, what are we going to get? Well, at this point here, I'm going to go ahead and simplify the inside of the parentheses of the factorial. So we have a 2n plus 2 factorial. Okay, so now let's go ahead and start rewriting the factorials here. If I started off with a 2n plus 2, then I need to multiply times the previous integer, which would now be a 2n plus 1. But now since I want to go ahead and reach the 2n factorial, I need to go ahead and multiply this times the previous term, which is now a 2n factorial. Perfect. And then this whole thing is multiplied times x to the n. All right, so we've simplified it here. Now let's see what cancels. On the top, I have an x to the n. Same thing as the bottom. It can cancel out. And I do see a 2n factorial in both the numerator and denominator. So that's also gone. And I think this is all that we can simplify. So let's see. Since we're going to go ahead and take the limit as n goes to infinity, let's see what we get. Once more, the x is not affected, so I'll take it outside of my limit, and I'm having the absolute value of x times the limit as n approaches infinity for, and again, at this point, since I'm only dealing with n's and they're all positives, I'm dropping the absolute values. So we simply have a 1 over 2n plus 2 times 2n plus 1 in my denominator. So what are we going to get? Since we want convergence, we want this inequality to be less than 1. But notice here that another funky thing happens here. If I were to take the limit as n approaches infinity, then this whole thing goes to 0. So what we actually have then is the following inequality. The absolute value of x times 0 is less than 1. Well, this is always true. So it doesn't really seem to matter what x is, because at the end of the day, I'm multiplying it by 0, and 0 is always going to be less than 1. So this is an example in which your radius of convergence is infinity, because it doesn't really matter how far away you're getting from your center, your inequality is always going to be less than 1. So if the radius of convergence is infinity, then the interval of convergence is all real numbers. Excellent. So now we've seen an example of each different type of scenarios. One where your radius of convergence is infinity, one where your radius of convergence is 0, and other ones in which your radius of convergence is a number that's greater than 0 and less than infinity. These ones here were the longest ones, since we needed to figure out what was the convergence at the endpoints. Okay, now I want to go ahead and take a look at one more set of examples that deals with the combination of power series. So let's go ahead and take a look. Now, because power series are polynomials, we can perform operations with them just like we can with polynomials, and the following theorem lists some of the possible operations that we can perform with these polynomial series. First, we can go ahead and combine them by adding or subtracting, which means that we can pull apart a power series that involves addition or subtraction. Second, if we have a particular power series and we want to multiply every term of that power series by x to some power, then we can go ahead and put that multiplication on the inside of the power series. Third, and very importantly, we can perform compositions with power series. Now remember, a composition means you have a function within another function. And this is going to be really useful in generating more complex power series, as we'll see in the next example. So let's go ahead and get some practice. In this example, we want to use the Maclaurin series for e to the x to find the Maclaurin series for e to the negative 2x and x to the fourth times e to the x. Now, in this problem, I'm going to do something a little bit different. Even though they're asking us to use the Maclaurin series for e to the x to find the Maclaurin series for e to the negative 2x, I'm going to go ahead and find the Maclaurin series for e to the negative 2x from scratch. Because I also want you guys to review, hey, how do we find Maclaurin series? Now remember, a Maclaurin series is nothing more than a Taylor series, it's just that it's centered at 0. Now, remember in previous videos that I mentioned that a quick way of coming up with a Taylor series or a Maclaurin series is by first writing out our original function, then taking successive derivatives here, which I guess I'll stop here in the third derivative, it would suffice. And then we're going to go ahead and evaluate them at the center, which in this case, again, Maclaurin series, it's centered at x equals to 0. Let me move this one here a little bit further down. So at x equals to 0, the original function is just going to be e to the 0, which is 1. Now, whoops, I am saying that we're going to be finding the Maclaurin series for e to the negative 2x. Now the coefficient is still 1 because e to the 0, well, it's still 1. All right, now, but for our derivatives, we're going to get here a negative 2 e to the negative 2x. Second derivative, we're now going to go ahead and get a 4 e to the negative 2x. And the third derivative is going to be a negative 8 e to the negative 2x. Okay, now to find the coefficients, so the coefficient for the first derivative at x equal to 0 is going to be simply a negative 2. Then for the third derivative, its coefficient is going to be a 4. Second derivative. And the third derivative, its coefficient is going to be a negative 8. Okay, well then the Maclaurin series for e to the negative 2x is going to be the following. E to the negative 2x is going to be equals to, and for this one here, just as a sake for review, I'm going to go ahead and list out, hey, how will the Taylor series be looking like? So we're going to have here f of 0 over 0 factorial plus f prime at 0 over 1 factorial times x to the first plus now the second derivative evaluated at 0 times x squared over 2 factorial plus the third derivative evaluated at 0 times x cubed over 3 factorial, and we will continue on with that pattern, which I'm now going to go ahead and start listing out, okay, what were the coefficients that we got? Well, we got the following. 1 over 0 factorial, don't forget though, 0 factorial is just 1, minus 2x over 1 factorial, plus 4x squared over 2 factorial, minus 8x cubed over 3 factorial, and we can keep on going. Now, with these 4 terms, I think we can come up with the power series representation for e to the negative 2x. So let's see, it seems like we can have the series as n goes from 0 to infinity of, well, in my denominator, I notice here that I have 0 factorial, 1 factorial, 2 factorial. So it seems like our denominator is simply n factorial. But what about the top? Well, I notice that there seems to be an alternating series here. So we're going to have here a negative 1 raised to the, now because my first power is positive, I'm going to go ahead and begin it here simply at an n. Now, I also see a 1, 2, 4, 8. So it seems like we're dealing with a geometric series on the numerator. So I'm going to have here a 2 to the n. Now, what about the x's? Well, it seems like the x's are only increasing in power by essentially an n. So there we go. This one here is our power series representation. But I do notice something though. On the numerator, I have all of the factors being raised to the n power. So I'm simply going to go ahead and rewrite it as the sum as n goes from 0 to infinity for negative 2x to the n all over n factorial. And boom, there we go. We came up with our power series representation for e to the negative 2x. Excellent. Now, why was I asking you to use the Maclaurin series for e to the x to find this Maclaurin series of e to the negative 2x? And this is where the theorem discussed above really shines. So let's go ahead and recall the Maclaurin series for e to the x, which we did in the previous set of recordings. So the power series representation for e to the x, or I guess specifically the Maclaurin series for e to the x, looks something like this. 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so forth, which could have been rewritten as the sum as n goes from 0 to infinity for x to the n over n factorial. Now I want you guys to notice that our formulas, they are very closely related. Specifically, the Maclaurin series for e to the x was the sum as n goes from 0 to infinity for x to the n over n factorial, whereas the power series representation, or the Maclaurin series representation for e to the negative 2x was a negative 2x to the n over n factorial. So it kind of looks like, more generally, we can think of the Maclaurin representation for exponentials as the following form. E to the u is equals to the sum as n goes from 0 to infinity for u to the n over n factorial. And this is why remembering some of the power series representation for common functions is very, very useful. Because if you know their formulas, you don't really need to derive them from scratch as we did in the previous example. Now again, just to emphasize the point, what if I gave you a new example, and I'll put here a bonus example. What if we wanted to find out the Maclaurin series representation for e to the x squared? Well, if we remember the power series representations for e to the u, then this one here is a very straightforward problem. We're simply going to have e to the x squared is going to be equals to the sum as n goes from 0 to infinity for x squared to the n over n factorial. And at this point, we can just go ahead and use the properties of exponents. And if we have x squared to the n, this is nothing more than x to the 2n. And there we go. All right, now this question, or this example, was also asking us to figure out what is the Maclaurin series for x to the 4th times e to the x. And just to increase the difficulty, let's make this one here x squared times e, let's say to, as we mentioned before, the x squared. All right, so let's go ahead and take a look. Now this problem, though, it's going to go ahead and use a combination of multiplication by a power and composition here. So let's see. If we have the x to the 4th times an e to the x squared, well, I'm going to go ahead and write it like this. This is going to be an x to the 4th times, and I'll go ahead and write down here the power series representation for e to the x squared, which we have on the side. And this is going to be the sum as n goes from 0 to infinity for x to the 2n over n factorial. Okay, now we can go ahead and take our x to the 4th, that's outside of the series, and bring it inside. But at this point, since you're going to go ahead and multiply two x's with different powers, the powers do end up adding. And our final result is going to be here, the sum as n goes from 0 to infinity for x to the 2n plus 4 over n factorial. Again, the in-between step being here, having an x to the fourth. All right, so this concludes our second part of the recording. In part 3, we're going to go ahead and take a look at derivatives and integrals of power series. I'll see you there.